All right.
It looks like another application is using the mic.
What?
Please close it, then try.
It's 2 p.m. It's time to begin. Good afternoon, ladies and gentlemen. You know, we always start from a question. Do you have any questions to me? You can ask. If not, please tell me what you think. Oh, sorry. Every time if you press the button and your clicker is set up to the right channel, you should see the green light blinks. If it's a red light blinks, you should reset the channel. That's it. If you need to clarify the question, you should raise a hand and ask your question. So that's how we communicate. You should apply your best effort, but everybody makes mistakes, so everybody who applies the best effort gets a large amount of correct answers anyway by the end of this class. So. Okay. You should be ready to press the button and tell me why.
I should be ready to?
Yeah, because you're late. And, well, you got to do something about it. Not you anymore. Yeah. The last person who enters the room, today at least, should tell me the reasoning behind the answer to this question. So please read the question, choose your answer, and tell us what you think. Test.
I really won't read that question.
You should press only once. You know, pressing second time or third doesn't help. It requests, it collects only the first response. That's it. You cannot change it anymore. The system is tuned up in such a way so you can press only once, and you can't change it. That means, well, talk to each other, reason it through first, and then press. So you ready?
I picked A because the slope is changing.
You picked A because the slope is changing, right? I'm just saying so everybody would hear you. Okay. You answered correctly to a wrong answer, to a wrong question. To this question, the answer is supposed to be which graph cannot represent. Yeah. If I asked you which graph can represent, well, of course, we know for the motion with constant acceleration, the position graph should look curved like a part of a parabola. So this graph does correctly represent the motion with constant non-zero acceleration. Non-zero is an important part of the question. But I asked which graph cannot represent the motion with constant non-zero acceleration. And this graph clearly represents the motion with zero acceleration. And this graph also represents motion with zero acceleration. So those two graphs violate the second condition. So B and C. It's about important of reading the question. What do we have to answer? So So, and again, my natural assumption is these people answered the question they've been asked, and these people answered a different question. Yeah? Sometimes, and actually it happens much more often than we think, we read or we look at something and our brain transforms it into something different, and we are answering a different question, not the question we've been asked. So it's just a good example of a similar situation. So read it carefully, and that's it. And this is what I want to do. This is a nice example. All right, moving on. That was a kind of review question. So now we're going to solve more problems related to different situations involving motion with constant acceleration. So for the first probably half of this class, we're not going to learn anything new. For the second part of this class, we're also not going to learn anything new, even if we might think we're learning something new. Well, that's an intrigue, you know. What's happening? You should do your work, I should do my work. And the work is reading, imagining, drawing a picture. Always the same steps in the beginning. So you're driving a car, you read your speedometer in miles per hour, and your brain, you quickly converting it into meters per second because you know how to do that. And you see a deer on the road in front of you. And that actually happened to me. So I know exactly how it feels. First of all, nothing happens instantaneously. Yeah. Everything takes time. It takes time to process. So the reaction time, well, for the average person is about 1 second. During the reaction time, your car keeps traveling at 20 meters per second. And only then you apply the brakes, and only then you start slowing down. So this motion is composed of two individual parts. And that's what should the picture show. The road, the deer, the car, you or me, it doesn't really matter. This is the distance from you to the deer when you notice it, 60 meters. It takes 1 second to react, 1 second. And starting from here, you're slowing down. The critical acceleration, which we're looking for, is such that you stop right in front of the deer, just barely kind of touch it. If your acceleration has a larger magnitude, you decelerate faster and you stop, before the deer. If your acceleration has not large magnitude enough, you're slowing down, you're decelerating, but still not fast enough, and you hit the deer. That's what's happening. So, right here. So, well, we can draw a kind of motion diagram. Yeah. The motion diagram shows several important locations. So, this one when we see the deer in the first time, this is when we start applying the brakes, and this is where we stop, just barely touching the deer, right? So please, tell me, how many meters did you travel before you applying the brakes? Exactly. So we know that this motion is composed of two parts. And we know that we have several types of motion. There's the motion with constant velocity, constant acceleration, and something general. And every time when we want to analyze a certain motion, we have to make a choice. What is happening? Well, in fact, as we know now, the motion with constant acceleration kind of includes motion with constant velocity. This is basically a case when acceleration is equal to 0. And for this situation, the distance traveled will be equal to speed times how much time it takes to travel that particular distance. So for the first part, we'll call it number 1. For the first part of this situation, 20 meters per second times 1 second gives 20 meters. That's an easy part, right? So out of 60 meters, you've traveled 20 meters first. Well, the picture tells us how many meters should we travel before we actually stop right in front of the deer. So how many meters should we travel? How do we know? Well, it's actually a combination of many abilities. We can see, we can read, we can think, and we can subtract. Not just, born with that. No, we've learned a lot of things, but now, because the total distance is composed of 2 intervals, this is supposed to be 60 minus 20, which is 40. And now we can basically forget about what we just said. The new problem starts. From here, with initial speed of 20 meters per second, you're reaching final destination and you stop over there. So final velocity, 0. How do we know? Stop, rest, all those words represent the same fact, v equals 0. Now, the distance traveled, the displacement, because in this situation there is no difference between the distance and the magnitude of the displacement, equals 40 meters. The question I want to ask everyone, please make your clickers ready. What is the direction of the vector representing acceleration? These are possible answers. The velocity is a vector, the displacement is a vector, the acceleration is a vector. So we have to add into our picture all vectors involved in this situation. If we do it correctly, it helps us to solve the problem correctly. Otherwise, we might make a mistake. Not necessarily we will make it, but might. So it's an important part of the reasoning. Please. You also should press a button. You also should press the button on your clicker.
Okay.
Did you?
No.
Do it. $93. That's the highest number I've got so far out of 110 students. So did you?
Yeah.
Good. Well, 88, that's a pretty high percentage. And again, if we look at the possible answers, only two might make kind of sense. Yeah, it is a one-dimensional motion. Everything is happening horizontally. So strictly speaking, we should choose only between these and that. So whatever else is happening looks strange. Now, the choice number 2 has a reason. Yeah, we might have read in the wrong way what's happening because it's slowing down. Yeah, the velocity and acceleration must be opposite. They can't be parallel. So speeding up means velocity and acceleration are parallel. Slowing down means velocity and acceleration are opposite. If velocity points to the right, the acceleration has to point in opposite direction to the left. So that's the acceleration. All right, now I'm going to stop talking, and please spend 3 to 4 minutes and calculate time. How much time should pass from the moment you're applying the brakes to the moment you stop? The question, the original question is about acceleration. We will answer that question as well, but let's try to do time first. So please solve it. If you need to remind equations we may use, you should raise a hand and ask a question, or you can print out the equation sheet for the exam number 1. Or you can use your notes, or you can use a textbook, or you can Google it, or you can ask your friend. So it's, but you should act. You should do something. You may be wondering who's Professor Duffy. Professor Duffy is another faculty here, and we borrow stuff from each other. So it's sometimes just easier to copy and paste instead of retyping every word. So, what equation can you use? This is the motion with constant acceleration. For that motion, we had a slide with, well, 2 slides. One slide had 2 equations, and another slide had 3 equations, 2 plus 1. So, you can't use equations for motion with constant velocity because that's not the case happening. You can't use equations for motion with relative velocities because that's not what's happening. So out of all possible equations to you, you have to concentrate on those 3. That's it. And you have to just write them down. This step does not require any thinking. It requires just searching either in the memory or in a notebook or online, and then you just copy those equations. That's the first step, no thinking. So the short equation has a name. How do we call it? For the motion with constant acceleration, one equation is short, one is long. The short one has a name. velocity equation. It's about velocity. So we can write the velocity equation. The second equation is longer. It also has a name. How do we call it? The motion equation or the position equation. So that's about motion and position. You write equations. The next possible step, not always the best, but always possible, is just plug it in the numbers and see if they work. So let's plug in all the numbers in each equation. Do we know the final velocity or final speed? So, well, I'm going to clean up this, actually. So, this equation, what's plugging in means substituting a variable with the number. And the rule is simple. If we know a number, we write that number. If we don't know a number, what do? So this is a situation, we don't know a number. What do? We stop and we give up, right? No. So what do? We write a variable, we write a letter, we just keep the same letter. So, unfortunately, that equation doesn't help us because it has two unknowns. So, what do? We close the notebook and we give up, right? No. So, what do? We tried another one, yeah? So, but we can't use it yet. What is missing in my picture? I've mentioned it once. Well, 155 of you were watching and 7 of you been here on a snow day. So 55 plus 7, 63. So 110 minus 63. Those people might not really know the rule. There is a rule. There is a forceful rule. Forceful. What's missing in this picture? Anyone? The object moving, it constantly changing position to describe the position mathematically. What do we need? What do we need? The position like X or Y or what do we need? Coordinates, axis, of course. That's a one-dimensional motion. We have to, no, we must do two things. We must choose a positive direction and we must choose the origin, 0. And of course, naturally, we would choose it at the initial position of the second part of this motion. The first part is easy, it's done. Now, now we can use numbers. X final, numbers I said. X final relative to this origin equals what number? X final, 40. Yes, you're right. X initial is 0. We set it to 0. Plus velocity initial, 20. Times time, we don't know. Plus acceleration, we don't know. Plus time squared, we don't know. Over 2. That's a straightforward application of the velocity equation and the motion equation. So what's wrong with this? Nothing. But we still can't solve it. However, we can solve them together mathematically. That's one way. There is another way, is using the third equation. I will show the third equation. We need to see all options. The third equation is, well, it has no name. It relates speeds squared. In this equation, final speed is 0. Initial speed is 20. 2 is just a 2. Acceleration is unknown. And the displacement from 0 to final equals 40. This solves the answer. Now about time. There are different approaches. If we know acceleration, we can go back to the velocity equation, and we can solve that equation for time. Or we can go back to the position equation, and we can solve that equation for time. Which is easier to solve, the velocity equation or the position equation? That's a quadratic equation. You have to know the quadratic formula. This is a linear equation if you know acceleration, which is what? Did you find? -5. That will give you the time immediately. So sometimes we can use different equations to solve the same problem. So we always choose which one? Anyone which comes first to mind. But I would recommend using easiest one. Now there is another approach which sometimes saves time. For the motion with constant acceleration, the graph for velocity as a function of time is a straight line like this. So on one hand, the total displacement over total time should be equal to what? Displacement over time represents a specific physical quantity which has a name. What name? Just velocity? Average velocity, and we cannot omit, we can't forget that first word. It's a part of the name, the average velocity, average. However, on the other hand, if we look at this graph, what is the average velocity? That's the value right here, between the initial and final. The initial, the final. So in this situation, for motion with constant acceleration only, the average velocity is also literally equal to mathematical average, arithmetic mean, which is, well, one number plus another number divided by 2. Again, this only works for the motion with constant acceleration. This works for any motion. That's a definition of average velocity. But if we combine these two together, what does it give us? 40 meters divided by time, supposed to be equal to initial velocity was 20, final was 0, divided by 2. What does it give us for time? 4 seconds, hence. And of course, we can check that using the acceleration we had here, -5, it also gives 4 seconds. So no matter how we solve it, if we solve it correctly, we always get the same results. Any questions? It's not just an example of how to solve a specific problem. It's an example of how to solve any kind of problem. Yeah? There is a strategy. Moving on, that's another example of the motion with constant acceleration. This example has a specific name. How do we call this phenomenon? Free fall. What do we know about the free fall? Well, one word, everything. But in other words, it's motion with a given constant acceleration. So here what's happening? The ground, the barn, I don't know, roof, something, yeah. So this is the ball, and we shoot. We not just release it, we actually toss it down. 12 meters per second. Distance traveled, 10 meters. And acceleration, well, let's call it 10. The magnitude so far. I can't say plus or minus because I don't see yet what? The axis. So I must show my choice of the positive y direction. That's the first step. And second step, I must show what? The origin, 0. Where do you want to? It's your choice. You said, where do you want it? Here. Okay. We have two natural choices. One normally is the initial position. Second normally is the final position or the lowest position. So this is not the most convenient choice, but since you said, okay, so it's his fault. Now, equations don't depend on our choices. The velocity equation still this. The position equation still this. What do we know? Well, we know the initial velocity. It equals to what? No? Negative 12. The initial speed is 12, but because of the choice of positive direction, the actual component is negative 12 meters per second. We know acceleration, A equals what? No? Negative. Well, you can choose 10, you can choose 9.8, that's not very important. What important is it has a negative component relative to positive y direction. Now, the initial coordinate equals what? Y naught, y initial equals? The gentleman far away? Of course, that's his fault. The final coordinate is equal to what? Minus 10, exactly. Because starting from 0, we would go up 1, 2, 3, but we actually go down negative 1, negative 2, negative 3, and we go up to negative 10. So it's 10 meters below 0. So negative 10. But now we know everything. That's it. Physics is done. There is nothing to think about anymore. You just plug in numbers and you answer everything you want to. For example, graph. Acceleration as a function of time. Well, it has to be negative 10. Just straight line, negative 10. Velocity as a function of time. It starts from negative 12. How does it go? That's an interesting question. If you start from negative 12, the velocity line, does it go up, remains horizontal, or down? Down, because it's speeding up. So the magnitude of velocity, speed, should increase in time. So something like this. What about position as a function of time? Well, it starts from 0. That's simple. And it goes into the region of negative numbers, so something like this. Which equation do you want to use to calculate, for example, how much time does it take to hit the ground? this equation will give you the answer. You know final, you know initial, you know acceleration. There's only one unknown here is time. But now, well, you got to solve a quadratic equation. So you should refresh your knowledge of how to solve quadratic equations. Any questions about physics? Physics is done. Yes? I've heard the words velocity, but I didn't hear anything else. So.
Could you explain why you have the line going down if it's supposed to be increasing?
All right. There are many possible ways to explain this. I would appeal to our knowledge of math in this situation. If you plug in numbers for the initial velocity and for the acceleration, that's a linear function with a negative slope. So for example, if you calculate the new velocity at t equals 1, it's going to be negative 12 minus 10 times 1, which is negative 22, so somewhere lower. One more problem, and what is happening is this. I actually have a picture. You are on the roof, you toss the ball, it flies up, it reaches, of course, maximum height. It always reaches maximum height and then falls down. But now it's actually falling down to the ground. So on its way down, it travels more distance, it takes more time to reach the ground. And basically, we need to calculate everything we can. We can calculate how much time does it take to reach the stopping point. How do we do that? We should use the velocity equation. From here, with velocity initial of 10 meters per second up to here, with velocity final 0 meters per second, and the acceleration relative to positive y direction equals negative 10 meters per second squared. The velocity equation gives us the answer immediately. That's what we call time up. 1 second. How can we calculate the total time? We have two options. The option number one, we can start from here with a new initial velocity 0, and we fall down. This distance is, so where's my picture? So this is my ball released from rest, from this level. The roof is 5 meters above the ground, and the ball was 5 meters above the roof, and now we also have this additional height it reached. That additional height, h max, well, is equal to okay, let's set the origin at the initial position again. So 0 plus initial speed times time up, 1 second, plus acceleration negative 10 times time up 1 second squared divided by 2. Right? So 10 minus 5, 5 meters. So from here to here, we have 5 more meters. So now, from here to here, it travels 5 plus 5 plus 2, 12 meters. we can calculate time down, yeah, applying the motion equation one more time. And then we can add time up and time down. But there is another way, physically simpler, mathematically more complicated. Again, that's the positive y direction. That's my 0. Relative to this 0, this final coordinate is equal to -7. That was the ball, 2 meters to the roof and 5 more meters down, -7. And that's my initial equals 0. So I can set up my position equation. Y final equals y initial plus v initial times time plus acceleration times time squared over 2. Now it's a total time from initial up to the final. So -7 should be equal to 0 plus 10 times total time plus -10 times total time squared divided by 2. So another approach. Which do you want to use depends on you. If you're very familiar with solving quadratic equation, if it takes less time to you, you can do this. Otherwise, you can do it step by step. First time up, then time down, and then add them up. Any questions? Questions once? Yes?
Your rounding acceleration takes gravity to 10.
In this classroom, I rounded up to 10.
But homework is test. We do 9.8.
On the homework, it's 9.8. On the test, it's 10.
If we use -9.8 on the test, we get things off.
No. It's just much easier to use 10. So you can, do some hard work and use 9.8, or you can do some easy work and use 10. All right, this solution. Now we start the new topic, the projectile motion. I said that we're not going to learn anything new because you know everything about it. So please tell me what you think about this question. This is basically an experiment like this. The ball rolls horizontally. Yeah. I'll take it. Thanks. And then it flies off. Starting from this instant, when it doesn't touch anything anymore, it is a free fall. We just call it slightly differently. We call it a projectile. It's been projected. Anything which moves like this is a projectile. And you know why this is important? Everybody loves sports. That's a projectile motion. This is a projectile motion. This is a projectile motion. Everybody who shoots from a huge gun or from I got more weapons. This is a projectile motion. Actually, is this a projectile motion? How do we call this motion? Circular, of course. But if the string breaks, this is a projectile motion. So, keep pressing. It's either 1 or 2 or 3 or 4. I'm still collecting your answers. What's important about projectile motion? That it's not a question. Horizontal motion and vertical motion happen independently from each other. Let's say I release 2 balls simultaneously. Okay. this ball, when it hit, flies like this. That's a pure projectile motion. This ball, when released, flies like this. The question is basically, how does the fact that it moves horizontally affect its vertical motion? And the answer is, oops, it doesn't. It takes exactly the same time to reach the tabletop. You cannot see it, it's too fast, but you can hear it. If you hear something like this hits first, this hits second. If you hear something like this, that first, that second. But if you hear this, what does it mean? Same time. So you can actually close your eyes. Where is it? So, what did you hear? Same. This proves the fact that the horizontal motion of the projectile doesn't interfere at all with its vertical motion and vice versa. What do we know about the vertical motion? That's a pure free fall. The acceleration down is same well-known free fall acceleration. But that acceleration has no horizontal component. So relative to the ground, if we looked at the shadow of that ball, that motion would have been motion with constant velocity. So the projectile motion is just a combination of two motions which we know. Relative to the vertical axis, that's a free fall, motion with constant free fall acceleration. Relative to the horizontal axis, just straightforward motion with constant velocity. And we know equations for both. We know how to describe both. So again, we have no need to learn anything new. When the projectile flies, the position vector changes. But every time it has two components. This component, x, undergoes motion with constant velocity. But this component, y, up or down, doesn't matter, undergoes motion with constant acceleration, and acceleration points down, and the magnitude of the acceleration is, well, about 10 meters per second squared. That's it. So, for the projectile motion, we have a set of equations we can always use to describe the horizontal part of the motion. We can use one simple equation. This is the motion with constant velocity. For the vertical part of the motion, we can use these equations. Same equations as we used before. Velocity equation, position equation, the third equation which has no name. We just have to use them simultaneously. This picture shows a very important fact. What is happening to velocity? First of all, in general, the launch velocity, the initial velocity, has a certain angle relative to the horizontal axis. That's what we call the launch angle. So initial velocity has two components. There is x component and there is y component. The x component is the one which we use, well, to describe the horizontal motion. And the y component is the one which we use to describe vertical motion. That's it. So we resolve the initial velocity into two components, and then we can forget for the moment about what's happening vertically and do the horizontal part. Then forget about horizontal part and do vertical part. And see how numbers work. Another important fact. You see what's happening to the vertical component of velocity. Oops. Last word. At the highest point, the vertical component of velocity becomes equal to 0. That's what the highest point means. But the horizontal never changes. All right, now we're done. Thank you very much. We'll pick it up from this on Friday. And let's see what you said. I'm going to save this.
Quick question.
Yes, so number 2, of course, was the correct answer. Yes.
The clicker that I normally use, I won't be able to get back for another week, and I'm borrowing some from somebody else.
Well,
Should I?
you should send me an email with your your new number, so I can see it in the system.
Okay.
So I can associate your name with the new number. That's it.
Okay.
And then you can send me an email again.
Thank you.
Sure.
I had a question about labs. I saw that we're using Logger Pro. Do we need to bring our own computers to lab or?
No. Why?
What?
No, of course not.
Okay, I didn't know if we
Why would-
supposed to use the software
no.
on our own computers or if there are computers there for us. Okay.
Of course. Yes. It's somewhere there. The attendance sheet, please. It's somewhere in the room. Who? Yeah. Oh, thank you.
Thank you very well.
Thank you. John, please. Some more. Yay. Yes.
I know, but do you press that every day? Because I've only done
Not every day. I just actually I forgot it only once.
this is the second time I've tried this.
You should. If you have any doubts, you should just send me an email and I can check. You can say.
We have to make up for that.
Is it a question or a statement? I'm not sure.
Do we have to make up for that?
Yeah, I mean, we
I
are
sent
in,
an email and it says you have 3 options. It's up to you which do you choose.
okay.
Okay, see the email.
You have 3 options. Number 1, do nothing. In that case, you just if you go to all other labs, you're not losing anything. Number 2, you can go today or tomorrow or on Thursday into any other section. Number 3, you can wait. And during the last week of the course, we always set up makeup labs for students who want to do it. And the snow day, of course, is an important reason. So if you want to do it then, you can do it then.
Thank you.
Thank you.
Was there something we were supposed to submit in order for you to verify that we were watching the lecture on Monday?
No.
Okay.
Hi,
Yes.
I'm Caitlin Mahoney. Just
Okay.
nice to meet you. So I'll go ahead.
Did you succeed logging to website?
I did, yes.
Okay.
But I noticed that my clicker wasn't responding when I was doing the answers, so I thought
Yeah,
I
I just shut it down.
It's okay.
If you said like a second before, I would.
Sorry.
All right. So on Friday, I suggest talk to me again. I will check your clicker.
Okay.
I think it might just need to be tuned up, to the right channel because different systems use different channels. This uses channel 21.
21.
And yours probably is 41 because most people use 41.
Okay. Okay, thanks.
Yes.
Oh, I just had a quick question about labs. So
Yes.
on the syllabus, we're allowed to miss 2 labs, right? According,
Well,
or did that change?
yes, it did. I sent an email about this. So now we physically have 9 labs left,
Yeah.
not 10.
Right.
So
Because my only thing is, last week obviously all the labs were canceled, and this week I can't attend. And I have labs Monday, and so I can't attend this week's.
well,
I have class.
That's why I've given 3 choices.
Right.
So if you miss the lab, you can do nothing about it.
Okay.
If you don't miss any more labs,
Right. That
that's
should be
it.
fine.
That
Yeah.
doesn't affect your grade at all.
Right.
If you can't go to any other section this week,
Right.
we will also set up, make up labs
Right.
by the end of the semester, and you can make it up later if you want to.
Okay.
If you by any chance missed another lab.
Right.
So in that case, if you make up
This one.
this one,
Yeah.
it will give you again 8 out of 9,
Okay.
which is a new number.
Right.
And you will be all set.
All right. Perfect. Thank you so much, sir.
Yeah, I think this and I think we're done.
Wasn't anything in 113, right?
I think what I know, she didn't ask for anything.
I just want to send it.
But sometimes she might